Is this how it works? Like, you know, for more formal meeting, you just control who can actually speak like this?
Yeah, exactly.
Okay.
Yeah, the way Kurt explained it to me is basically, if any person logs in with that link, it's like their ticket into the room, but they're in the audience. And then he, as the organizer, can pick people out of the audience and put them on the stage, at which point you're able to share your screen and video and mic and all that. So everyone else, they can only watch and then write some text into the chat.
Okay. It requires somebody to monitor this, I guess. Yeah.
Sure, yeah. And then at the end, it'll open up for questions.
Okay,
which I think, yeah.
You're live on YouTube.
Great.
Right.
The attendee list is growing.
So Ben, maybe I will start.
Okay.
And then you can switch the slide once I start speaking.
Yeah.
Okay, you're good to go, Ben.
Okay.
Okay. Well, good morning, good evening, everybody. Thank you all for coming from such different time zones, spanning the whole world almost. It is really my sincere pleasure to introduce Ben Bow. He is my first PhD student since I've joined the IFA. He's also my first PhD student who had the courage and the foresight to exploit eclipse observations for exploring the physics of the corona. He has completed 3 original and different research projects, tapping into the unique wealth of these observations. I'm also pleased to announce that Ben has just been awarded an NSF Postdoctoral Fellowship, which will be hosted at the IFA. He will assume the role, most likely, of a lead solar wind Sherpa and will be collaborating in addition with Cooper Downs at Predictive Science, who was also a former IFA grad. So who is Ben? So, is he a future astronaut or a beach bum? Okay, next slide. So let's just look very quickly at Ben's CV. So he got a master's in, his bachelor's from the University of Puget Sound with
Puget Sound, sorry.
Puget Sound, sorry. Cum laude in honors in physics in 2015, and then he got his master's in astronomy in 2017. But by the end of his master's, Ben had almost slipped into the dark side. He had started a project with Rob Jedicke, Rob, no offense, and they published a paper. But, and also in his early years in graduate school, it was clear that he had developed a taste for travel. And the first were to classy places like Japan and France, Lyon. But then things got different. He became more exotic. He went to Indonesia in 2016. This was for the eclipse. And we had to travel by air, water, and land. So it was quite an adventure. But the challenge was substantial, especially after he had just had a bike accident before we traveled. So he came into the IFA, into the lab with a bandaged hand, and his helmet had broken. So I was really worried that he might not be able to go with us. But he brought along all his equipment to take care of his wound and the necessary pills, antibiotics, and whatnot. Okay. Now, Ben had also visited large telescopes, and I'm not exactly sure what went through his mind, but it's clear that afterwards, he decided that the smaller ones had more appeal. So he finally saw the light, and he ended up becoming a solar wind Sherpa. He did beautiful work with eclipse observations. He's the first who has really tapped into them and was able to infer some very nice quantitative measurements. And he ended up with 3 publications, 3 referee publications. So the first one was already published, I think. So bandage or not, Ben was happy to have discovered the corona. So without further ado, Ben, please go ahead.
Great. Thank you, Shadia, for that great introduction. Yeah, so I'll be talking about the work I've been doing over the last few years. And of course, it's about the solar corona, which we see very beautifully in an image like this. But before I talk about the corona, I'm actually going to jump in and talk just about the sun generally. So if you look through the sun with a small telescope like this, I actually took this photo myself with a cell phone camera through a lab telescope with a filter, of course. And if you do this, you see the photosphere, which is by definition this optically thick surface on the sun. And you'll see features commonly like sunspots and granulation and things of that nature. And of course, this is what Galileo did in the 1600s. He was really the first to, I guess, scientifically identify sunspot and sunspot groups. Not only that, but if you actually play a time lapse of his daily observations, you can clearly see the rotation of the sun. So he's often credited with sort of discovering that the sun is actually rotating. And so, yeah, this is basically the state of solar research in the 1600s. If you fast forward 400 years, now we can make really high resolution images of the solar surface, like this one from DKIST on Maui. And you can then play a video of this. And so you can clearly see these convective motions in the outer layers of the sun. Of course, you can use this sort of data to study sunspot regions and the photosphere and the chromosphere and all this kind of stuff. And in this region of the sun, you do have motions, these convective motions, you have oscillatory motions. But if you consider on the scale of the sun itself, these motions are rather small. So one can basically just consider them as oscillations around an equilibrium and more or less consider the sun as a fixed object. Of course, if you look at the sun spectrum, you see the nice characteristic Blackbody curve, which is indicating that the sun is rather hot. And then this is carved out by absorption lines in the outer atmosphere of the sun. And if you study all of these lines in the Blackbody continuum, you will learn a lot about the composition of the sun, as well as the temperature, which you wave your hand and say is about 5,800 Kelvin or so. And so, you know, great amounts of research that all of we do in astronomy, a lot of is focused on this sort of data. Another thing you can do is study these spectral lines in a bit more detail, say look at the polarization and line splitting through the Zeeman effect, and you can use that to study the photospheric magnetic field. So here's an example from SDO HMI data, where on the left is just the pure intensity of the solar photosphere, and on the right is this inferred magnetic field strength. And you can tell that where the magnetic field is strongest is correlating with where these sunspot groups are occurring. And so, of course, we know now that these are what we call magnetically active regions. So you have these sunspots on the surface, and then above them in the lower regions of the corona, you'll have sort of these closed field lines that will emit in the extreme ultraviolet. And so now we will observe in the EUV commonly in order to study these things in more detail. So let's talk about, well, what kind of data can we get from the EUV? Well, obviously the EUV is very, very high energy photons, and they are absorbed by the Earth's atmosphere. So you really have to go to space to observe it properly. And they're very useful for showing the lower regions of the sun, and a number of spacecraft do this now on a daily basis. But there is one major drawback of EUV analysis, and that is that the lines, the spectral lines that you're looking at in the corona here are not excited in the same way that the photosphere is. Instead, you're dealing with a collisional excitation. So essentially, these are higher level transitions that require high amounts of energy that the photosphere cannot supply. So instead, you have collisions between electrons and ion populations, and this will then excite lines that emit. Now, that means because you require a collision, it means that the intensity will be proportional to the density squared. So therefore, in the low regions of the corona where you have really high densities like these active regions, this sort of data is extremely useful, and tons and tons and tons of research gets done on that sort of data, and that's great. But, and also just this process is very different than the kind of Blackbody and absorption line features that we see in the photospheric spectrum. So if you try to probe as far as you possibly can in the EUV, like this from Proba 2 to European spacecraft, and in this way, you can actually see maybe about 2 solar radii or so, meaning 1 solar radius above the surface. But you can tell, though, that this emission is somewhat tenuous, and it's only really tracing the highest density regions in the corona. So again, it's useful for certain elements of things to study, but it's not a complete census of that region of the corona. So the other technique is, well, why don't we block out the photosphere and instead try to understand say the outer corona of the sun? Now you can also do this, say, from the ground and look at the lower corona, but then you get limited by the sky brightness of the atmosphere, of the Earth's atmosphere. So it's easier then maybe to go to space and do something like what LASCO does, again, on a daily basis. And this shows the outer regions of the corona. And not like, unlike the UV, this type of emission is coming through scattering processes. So you get, say, Thompson scattering by the electrons, which will scatter photospheric light. You also have radiatively excited emission from various ions in the corona. And these sorts of effects will depend instead linearly on the density. Therefore, you're able to see them at much lower densities and much higher distances from the sun. But of course, this data also has a substantial drawback, because you're limited in how close you can get to the sun, especially for the space-based coronagraphs. So if you take the best data available basically on a daily basis and you process it, you get images like this. And these are great data sets, and lots of work can be done on, again, on active regions, on CMEs, coronal mass ejections, and other dynamics in the corona, and that's great. But if you try to stitch these two data sets together, you'll see there's sort of a glaring gap between them that is really not observed on a daily basis. Now, some might argue that in future instrumentation could probe this region, but I would say, at least at present, it's basically unobservable, at the very least under-observed. Now, however, when a total solar eclipse occurs, you can very conveniently connect in between these data sets and probe this region of the corona that normally is very difficult to study. And because it's so difficult to study, we really don't understand it as well as other regions of the sun. So of course, a total solar eclipse occurs when the moon comes between the Earth and the sun, and it conveniently blocks out a little bit of tiny patch on the Earth where the sun is totally blocked out. And essentially, this is just a giant coronagraph. And because it's so enormous, we can get around some of those light diffraction effects that will plague a regular coronagraph. And of course, this sort of diagram is highly not to scale. Just to give you some reference, here is actually the Earth-Moon system to scale. And by this scale, the sun would be way off on the other end of the room. So the point here is that because the moon is so far away, it's good to act as a coronagraph. But the downside is that the moon's orbit's slightly inclined. So this sort of alignment doesn't actually happen all that often. It happens about once every year and a half, and it only lasts a couple minutes. So it takes quite a lot of effort to travel to some arbitrary location on the planet once every year or two and make these sorts of observations. But if you do this, you can study a lot of things about the corona, and really some of the fundamental observations that gave us our basic knowledge of the corona came originally from solar eclipses. So probably the most famous example is this 1879 eclipse, where Professor Charles Young traveled to an eclipse and took an image of the corona through a prism. So all he really had was a prism and a photographic plate, and he measured the spectrum, slitless spectrum. On the right there is an image of a modern recreation of what this experiment looked like. And what he found was this line in the green, which had never been identified before. And so at this period in astronomy, we of course did not understand quantum mechanics, but we did have chemists that were in labs, and they were burning various things and telling us, oh, I see this line, that line from various elements. So we had a sort of a system of identifying what are things made of in space at a fundamental level. And so this was a common practice. In fact, or rather, so when you observe something in space that you hadn't seen yet in the lab, you just called it some new element. So in this case, they named it coronium. And this was not at all unprecedented. In fact, helium was discovered very much in the same way. Actually, during a solar eclipse as well, it was seen in a chromospheric line into prominence. And so it was very common to just name some new element. But in fact, what we realized several decades later was that this was not some new element. But with the power of quantum mechanics, we realized actually it's a well-known element of iron that had been ionized an exceptional number of times. So this is iron 13 plus. And for reference, iron in its neutral state will have 26 electrons, meaning that this element, or rather this ion, has lost half of its electrons. which is a lot. We didn't think this would be possible. And that's part of the reason why it actually took a decent amount of time after quantum mechanics came around for us to realize what this was. So what this actually implies is that the corona must be at least 1,000,000 degrees Kelvin, because that's the only way you can pump enough energy into these ions in order to strip them that many times of their electrons. So putting sort of all this information together, you sort of, this is, by the way, a stitching of data between AIA and solar eclipse data. So you sort of get the photosphere and you say, okay, that's about 6,000 Kelvin. And then just above that, you have the corona, which is on the order of 1,000,000 Kelvin. And so obviously that's a very rapid rise in temperature. If you make more detailed observations and figure out what the temperature distribution looks like, you get something along these lines, where you have a very rapid rise in temperature in the very lower regions of the, say, chromosphere transition region up into the corona. And then it actually stays relatively flat in, say, the middle regions of the corona out to a few solar radii. In fact, it'll keep decreasing as it goes out into the heliosphere. And these first inferences of this profile really came from ionic observations during eclipses. Another thing you can do is look at the polarization of light coming from the corona and use that as a way to infer what the density of the electrons is in the corona. And this is due to the way that the light is scattered. And if you do this, which was commonly done about 100 years ago or so using polarization observations at eclipses, you get a density profile that's dropping very rapidly with distance in the corona. And so the combination of these two observations, which originally came from eclipse data, is very fascinating. It's telling you there's an incredibly high temperature, incredibly steep drop in density. And these two components together, if you work out the hydrostatic equations, as Eugene Parker did in the 50s, what you come to the conclusion of is that the corona cannot be bounded. It has to actually be flowing outward. And so he coined then the term the solar wind, that the corona must expand outward into space. And he's often given credit with sort of having discovered or inferred that the solar wind must be in existence, but really it was actually inferred before that by Blermann earlier in the 50s. And he did this actually by looking at very nice comet observations of that period. So this is actually a modern image of comet Neowise, which we've all been hearing about in the news, I'm sure. And what Blermann noticed is that these comets often are two different tails. One is this dust tail that's not as well structured, and it sort of follows the orbital momentum of the comet as it's coming through the solar system. Now, of course, you have radiation forces and other things that are pushing the dust around, but it still curves in the direction of the orbit. Whereas you have an ion gas tail, which tends to be much more structured and also is going exactly anti-sunward. And so Blermann inferred there must be some flowing of particles from the sun in order to push the ion tail in this way. And of course, now we know what's happening is that these particles are slightly ionized, and so they're locking on to the solar wind's magnetic field and being carried away with the solar wind. And so you might ask, well, why should we care about all of this, that there is a solar wind and that the corona creates it? Well, fundamentally because the corona and the solar wind directly impact the Earth. Very famous example of this, of course, is the aurora, which is the collision of these particles with the atmosphere of the Earth, and it gets dragged to the magnetic poles of the Earth as it locks onto the Earth's magnetic field. And normally this thing is rather benign, but under very extreme circumstances, like a large coronal mass ejection, it can overpower the Earth's magnetic field and actually can cause power outages on the surface. Very famously, in the mid-1800s, there was the Carrington event, which aurora was seen as far south as Hawaii, which that sort of event today could potentially cause very massive damage to our power grid. And then also, if you're wanting, say, to travel and go colonize Mars or something, or travel throughout the solar system with robots and or humans, you should understand what kind of weather, or space weather as we call it, is existing in the heliosphere, and not only necessarily how to protect from it, but also how to predict it. So this brings me sort of to the goal of, well, what was my goal to contribute to this quest? And so the basic idea here was, okay, we have this region of the corona that's underexplored, yet it is a very crucial region for defining how the solar wind forms and evolves. So wouldn't it be great if we could use, say, eclipse observations to better understand this part of the corona? And so you might ask, well, what are the main physical parameters that define the corona that we could observe? First, obviously, is the density. But as I mentioned before, this is actually very well studied, both from eclipse and coronagraph observations using polarization observations. So this was not really a topic of my thesis because it's sort of basically pretty well characterized already. Next thing was the ionic freezing distances, which I'll talk about what that means in a minute, but that was one project from this thesis. Another was to better quantify the temperature in the corona, specifically the electron temperature. And then finally, to better understand the structure of the magnetic field in this region of the corona. So, but before I get into all the juicy science, I should discuss these instruments that we use and how this works. Part of the reason this is so important is because, as I've sort of mentioned, traveling to an eclipse is very challenging. And so you only have a few minutes. You have to go to some arbitrary location on the globe, traveling, you know, as Shadia said, often by air, land, and sea. So this requires, in a sense, a fleet of small, portable, and robust instrumentation that you can set up on site and make these simultaneous observations. So one type of instrument we have are these white light telescopes, which are exceptionally simple by astronomy standards. It's basically just an off-the-shelf hobby telescope with a really nice, say, Nikon D800 type camera at the back. So that's rather straightforward. So I'm not going to talk about those really. But the narrowband telescopes are also very important, and those are used to measure the actual line emission in the corona, like that 1800s eclipse to measure the iron 13 plus. And so because these narrowband telescopes are a bit more complicated, it actually takes a decent amount of work to operate them, to calibrate them, and correct for various effects of the instruments. So the way that these work is we have Fabry-Perot filters that we put at the front of these narrowband telescopes. And if you don't know what a Fabry-Perot filter is it's an interference filter. So it's essentially an oscillation cavity where it lets a little bit of light through each time. If you're the correct wavelength, it'll constructively interfere and pass through the filter. If you're the wrong wavelength, it'll destructively interfere and basically disappear. And so this is a powerful method for isolating a very specific wavelength. And what we do is we have these designed for about half a nanometer wide bandpass at the front of these telescopes. Here then is sort of a cartoon level optical drawing of what this looks like. It's not at all to scale, and it doesn't even include all of the components, but it's sort of just to give you a sort of an assembly of black boxes to give you an idea what's going on. So we have the incoming light, which is A there, which then goes into the Fabry-Perot filter, which is C. And it's also important to note that the Fabry-Perot filter can be altered by the temperature and the precise angle. So we actually have a heater assembly that keeps it at a very precise temperature, precise to about 0.1 Kelvin. Then after it passes through that filter, it goes through an achromat lens that focuses the light down. And in fact, the achromat lens is really an assembly of two lenses together. Then it passes on to this CCD detector where we actually make the observation. And this detector is essentially a high grade, off the shelf consumer grade camera meant for like astrophotography and that type of thing. So this is now an image of what these telescopes actually look like. Panel A there is actually in the same orientation as this cartoon drawing was here. So we have the heater assembly is that silver bit, which is shown in panel C as well. And then the Fabry-Perot filter is inside of that. In panel B, you have the achromat lens on the left in the telescope tube there. And then on the right is that red thing is the CCD, which is also cooled. So then we take these cameras to on-site and we have to mount them, often several, or not several, but a few of them on a single mount, which takes some work to co-align. And then once it's co-aligned, we can make observations. In panel A, there is actually me in Indonesia making some calibration observations. Unfortunately, the data from that eclipse, it was too cloudy to be used. And then panels B and C are from Nebraska in 2017. And you can see Gary Nita there in panel B from Maui. And he is helping with the co-alignment there. And then in panel C, we're all in the observing tent where we actually are during the eclipse. So I've sort of mentioned these these line emission observations that we want to make, but it actually is important also to measure the nearby continuum. And this is because the brightest part of the corona is not the line emission, but is actually a continuum source. So you have this Thompson scattering of electrons, which I discussed before, and that's what we call the K corona. We then also have dust scattering, which we call the F corona. And the combination of these two different continuum sources is actually quite a bit brighter in general than the line emission. So another element that's important to consider is that the K corona is color neutral. And this is because Thompson scattering, or rather electron scattering, really doesn't care what wavelength you give it. It'll equally well scatter that light. Whereas the dust scattering will preferentially have a wavelength dependence. So it'll become brighter at redder wavelengths. And then, of course, the Earth's atmosphere itself also changes the color due to Rayleigh scattering. So because of these elements, it's important to measure not only measure the continuum, but measure the continuum in a nearby location to your ionic observation. And so that means for every ion that we want to observe, we have a secondary telescope that measures the continuum radiation in a nearby wavelength. So one way we've achieved this is actually to make identical filters and then actually tilt the heater assembly 7 degrees in order to shift the central wavelength of the filter. And a couple of the telescopes use this tilted design. We also had one where it used the normal design, but simply had a different filter manufactured for it at a different wavelength. If you then look at what the actual band passes of these filters look like, the gray line there is this iron 13 plus line, the very famous one I talked about before. And we have a number of filters designed to study that line specifically. We then have, say, those tilted filter ones are the identical filters, but shifted via the tilting of the heater assembly. And then finally, we have a unique filter that's quite a bit further to the blue. And also on the top there is the radial velocity of how far away these filters are from the central wavelength. Here's the same sort of plot, but for the other line that we study, which is the iron 10 plus line. And these two lines are the ones that I'll use for the analysis in this thesis. Another caveat is that, of course, we need some calibration between these observations because they're independent telescopes. It's so in that sense, it's a bit more complicated, say, than maybe a professional level telescope where you're using the same instrument the whole time, so you can just calibrate that instrument. Instead, we have to cross calibrate instruments. And so in this way, what we do is actually observe the solar disk through an additional neutral density filter. And the purpose of that filter is basically just to make sure that we don't damage the instrument, because obviously the photosphere is very bright and we could damage the detector or the instrument if we did this. So we use the exact same additional filter on the front, and we observed the sun within a few minutes with both the on and off band observation, or rather both the on and off band telescope for a given observable. And then what we do is integrate the solar disk brightness and use that brightness to cross calibrate the pair. Okay, so now I'm going to move on and actually start talking about the science that we can do with these observations. And so the first project I did was to quantify the freeze-in distance in the corona, again, using these two lines of iron, using data from the 2015 solar eclipse in Svalbard, Norway, which actually was before I joined the group. So before I jump into what I actually did, it's important to explain what do I mean when I say the freeze-in distance. We'll go back to this plot we had of the density in the corona. And above that, I sort of have a cartoon depicting what that might look like if you would see the particles. And so in the low corona, you have a very high density and lots of collisions. And that means that between the electrons and the ions, there's lots of collisions. And so an ion can maybe gain or lose an electron in its orbital structure, depending on the energy of those collisions, which basically means the electron temperature. And this will drive changes then in the ionic distribution. Far away from the sun, though, say, with several solar radii away from the sun, you have a rate of collisions that's essentially zero. And that means that whatever state the ion is in, say it's iron 13 plus or iron 10 plus, whatever state that is, it'll be that state forever as it flies out into the heliosphere. And so that means if we're at 1 AU and we have a detector that's measuring the ions in the solar wind, this ratio of ions that we see is telling us what they were in the lower corona, specifically at this distance we call the freeze-in distance, which is the delineation between essentially this collisional and collisionless environment. Now, this distance had been predicted through modeling, but never had been observed before. So the goal of this project was to be the first to actually infer what the distances were in the corona using some real data. So you might ask, well, why is the freeze-in distance important? Why do we care? Well, so we have ionic evolution, as I said, through these collisions in the low corona, and this will continue in some way up to the freeze-in distance. And beyond that distance, whatever you're seeing in situ will represent what the conditions were when they passed through that freezing distance. And so in that way, if you know what's going on at the freezing distance, you can predict exactly what the in situ detector is seeing. Or rather, it offers a way in perhaps a data-driven sense to directly link what's in the corona to what you see far away from the sun in the solar wind. So just how did we do this? Well, again, here are our observables. So we have this on-band image of the line emission, and we have this off-band image. The off-band image is going to basically be proportional to the electron density, whereas the on-band will be proportional to the combination of the ionic and electron densities. And so actually, even without a calibration in this case, you can take a ratio between these images and it'll be proportional to the ionic density. So in that way, you can just take the ratio of these two images and along, say, a magnetic field line, you can measure what is the relative ionic abundance. So if this value is fluctuating, you would infer, okay, it hasn't frozen in yet because the ion population is changing relative to the electrons, meaning it's either ionizing or recombining. However, if this value becomes fixed, you can then say it's frozen in. And so this is exactly what I did by hand drawing lines through the corona along magnetic field lines and measured what this value was between the images. And then I had an automated algorithm that determined where precisely this line became consistent with a flat slope for the rest of the data. And so I inferred it again and again and again over many hundreds of lines through the corona for both the iron 10 plus and 13 plus lines. And so you can see there, each one of those is an independent measurement with some uncertainty defined based on how well it could fit a flat line to the data. Then combining all this data together and putting it on top of the white light image and of course interpolating the data points, you get an image like this, where you can clearly see that the freezing distances are not the same between the two different ions, and they don't occur at the same distances for different structures in the corona. So let's walk through this a little bit. In the polar regions of the sun, where commonly you have what we call a coronal hole, and coronal holes are known for having a lower density, lower temperature, faster expansion speed. And in these regions, we find that the cooler line, the iron 10 plus, was freezing in further out than the hotter one, but both were freezing in pretty dang close to the sun, much closer than what was predicted by models. Next, in sort of what you might consider a normal-ish streamer region, you have the exact opposite behavior, where the more higher energy, or rather the hotter temperature ion, the iron 13 plus, was freezing in at a further distance, and both were slightly shifted outward on average from where they were in the coronal holes. Next, you actually had a coronal mass ejection that erupted about 10 hours prior to the eclipse. And in the wake of this CME, that was this wedge basically that was left in the corona, in that region, you had behavior very similar to the coronal holes, where the cooler line was freezing in further out. But yet both were shifted quite a bit outward compared to what they were in the coronal holes. It's also worth noting that actually in the middle of that wedge is a little streamer that had reappeared just prior to the eclipse. And over that streamer, you saw the behavior sort of going back to what it is in the other parts of the streamers. Next, above these prominences, where you had streamers as well, but right above these larger prominences in the corona, you had behavior similar to the other streamers, yet an overall offset outward. And then finally, in this other region in the top left there was a rather large prominence, and based on the white light data, it looks as if there were some rather large closed field lines that extended out to at least 2 solar radii. And in this region, we had some very confusing data. It didn't really make sense. And so basically we inferred that the iron 10 plus probably hadn't yet frozen in. It's unclear whether the iron 13 plus really did or not. So in that sense, we sort of just throw out the data from this region in our discussion. So basically binning this data from those different morphological regions that I identified, you'll see that the averages in these regions is statistically different quite a bit between some of the different regions. And these differences are significant as well between one ion and another in the same region. However, the precise cause of these differences is not entirely clear. It could have something to do with the electron density, with the temperature, perhaps with other elements, magnetic field strength, potentially, you could come up with some idea maybe from modeling why this is the case. So really future modeling should try to be informed and constrained potentially by these numbers and see if they can explain why they're so different. But sort of the motivation I had then for the next study was looking at this. I thought, well, there seems to be a correlation with what the temperature of these structures is typically known to be with what the freezing distances were. So wouldn't it be great if we could actually quantify the temperature in the eclipse data and then potentially combine these two methods together? So that led me to the second project, which was to infer the electron temperature and actually also some serendipitous time variation. And this was done using the 2017 solar eclipse data, which I helped to collect in Nebraska. And again, the same basic observables here, the iron 13 and 10 plus lines. And in this case, actually just prior to the eclipse, there was a small CME that erupted in the corona. So on the left there is a differenced image of AIA, on the right is of LASCO. But the one on the left there, that's a few hours prior to the eclipse up to just about right before the eclipse. And what you see is there was an active region labeled by arrow number 1 and a prominence, arrow number 2. And the combination of these two structures sort of erupted together to create a CME that was in the middle region of the corona that we see during an eclipse at the time of the 2017 eclipse. So arrow 3 there in the LASCO data is showing you that the motion of that CME in the LASCO data. And that's basically during the eclipse where the CME was. There were also some other motions labeled by some of the other arrows, including a disk center active region at arrow 7 there. So we think there actually probably was an element of a halo CME as well. But if you look at this data and say compare it to average data of this type, you would not necessarily think this was a very large CME, and this sort of motions will occur often multiple times a day. So during this time, though, of course, we had the 2017 eclipse, and we had one with 3 different sites that returned usable data on this narrowband observables. The first one was in Oregon at 1722, and then we had one in Idaho about 9 minutes later, and then in Nebraska almost half an hour after the first eclipse in Oregon. And so what I could do is repeat, basically do our inference using the eclipse data and do it again multiple times across the path of totality, giving us a time baseline. So first was to take the line to continuum ratio, and clearly you can see that the structure between the hotter and cooler line is quite a bit different, and this is entirely expected based on what you might expect the temperature distribution in the corona to be. But what was really cool to see is as well that there were quite a bit of change between the two sites here, the top row being the Oregon data, the bottom being the Nebraska data. If you actually look at this data in closer detail, actually what changed, on the left, you have the change in the delta log of this ratio. On the right is the exact same change, but shown in units of how, rather shown in units of the uncertainty of the data. And this uncertainty is coming both from the photometric and calibration errors. And so basically what was going on is the iron 14 appeared to be increasing in intensity in the streamer regions and sort of decreasing elsewhere. Whereas the iron 11 was sort of increasing everywhere, except for perhaps the low corona, and very, very pronounced increase at the location of where the CME was in the corona, which you can very clearly see in the sigma image in the bottom right panel, which is the bottom left side of the bottom right panel. So then, of course, but as I said, the motivation originally of this project was to measure the temperature actually. So then what I did was actually to measure the line ratio between these two different ions and then do some calculations, which I can talk about at the end if you're really interested, but for the sake of time, I'll just skip over some of the methodology here and basically say we just inferred the relative ionic abundance of these two different lines. And if you know anything about the electron temperature, you'll know that at different temperatures, you get a different abundance of these different lines, or rather these different ions. And so if you take the ratio of these two curves, you actually get a monotonically increasing function that tells you over a reasonable range of temperature what the relative abundance of these ions corresponds to as an electron temperature. So I fed those relative abundance ratios into this temperature functionality, and you get then a map of what the electron temperature was in the corona. And we have values that seem relatively reasonable, where in the coronal holes, it's about 1.1 million Kelvin or so. In the streamers, it's closer to 1.4 million Kelvin. And I will note at this time that I'm not necessarily claiming that these are the precise kinetic electron temperature, but rather this is a density weighted line of sight average of what the plasma temperature was over this region. So for example, if you have different structures along the line of sight that have independent temperatures, you're going to add up the light from all of those different structures. And so your final inferred temperature is basically telling you what's the average of the temperature distribution. So there could very well be 2.5 million Kelvin regions right next to 1 million Kelvin regions. And so the average of that is going to be somewhere in between. So these values don't necessarily represent precise kinetic electron temperatures. But regardless, you're still measuring a self-consistent metric of what the average temperature was. And clearly between these two sites in Oregon and Nebraska, this value did not stay exactly the same. If you look at how it changed, it appeared to actually increase in the very low regions of the corona, whereas it decreased in the outer regions. Again, the top being the delta in temperature, and those deltas typically at most were about 100,000 Kelvin over a half-hour period. And then in the bottom is again in units of the uncertainty. And so you can clearly see that the some of these changes are greater than 10 sigma significant. Some very prominent ones, or rather, a very prominent change occurred. You can almost see like a jet-like feature in the south polar region. And that's studying this region is something that one of Shadia's new grad students, Sage, is currently working on. But anyway, the point is that in this data, you see that there are clearly some substantial changes. It appears almost to look like a halo type shape, perhaps some motions likely due to the CME activity that was occurring at the time of the eclipse. Another piece of evidence to support this idea is actually that we were able to quantify some Doppler-shifted line emission. And this was completely by accident. And actually figuring this out was a bit the bane of my existence for a number of months. And it was because with these continuum imagers that I talked about before, if you recall, some of them were achieved by having these tilted filters. But what we realized was that those tilts were not enough. It only shifted the wavelength 550 kilometers per second in Doppler space away from the line center. And if you know anything about the solar wind and coronal mass ejections, you'll know that that speed is actually in the ballpark of where you might expect a CME to reach in, say, the first few solar radii. Maybe right at the edge of what we could maybe observe. But what you clearly see is that thankfully we had some other observations. And again, I can talk about this at the end if you'd like. But basically, I was able to actually use these contaminated continuum data to instead measure what the Doppler shifted line emission was. And so what we found is very clearly on the left-hand side there, which is where the CME was, that you saw a very pronounced amount of Doppler shifted emission, meaning it's coming at the observer. So this CME was likely erupting not only towards the left, but also towards the Earth, probably at some angle. And so we're able to capture some of this plasma as it's moving through the corona. So just to put this all together, basically what we're seeing is CME-driven changes in the temperature distribution in the corona. One potential interpretation would be that as the CME is leaving the corona, you have the density decreasing. And this is because the CME potentially would increase the density initially, but by the time of Oregon, the CME had already passed through a decent amount of the corona. So really we're seeing the corona already in a perturbed state. Then this expands outward. And so we're seeing, in a sense, the after effects. Perhaps the density is decreasing. Maybe these closed field lines near the solar surface are resisting this expansion. Potentially could cause alvenic heating or something of that nature, but it could also simply be that the open field lines are preferentially having plasma get thrown away, whereas the hot field lines are just staying the same, in which case you would infer a temperature increase. So again, this is not saying that the kinetic temperature changed, but rather that there were motions in the corona that were driving a change in the temperature distribution. Okay. So now I'll move on to the final study, which just was pretty recently finished. And the motivation for this study actually came out from a number of conference talks that I saw, or papers as well, where I would see people do some great, MHD model, some great model of the corona and saying, this is what we predict the corona should look like. And then they put it next to an eclipse image. And then they would spend 10 minutes just talking about qualitatively, how is this image the same or different than the model? But then everyone would say, this isn't good enough. We need a better way to quantify this. And so what I realized was that in this eclipse data, there really is imprinted a very high resolution counting of what the structure of the corona looked like. And this is telling you basically what the magnetic topology is in the corona over many, many years. So here's an just example of some of the data that was used as part of this study. So what I did then was to apply a new algorithm, which was actually developed by Clark et al. In 2014. And what Clark did was actually to develop this method specifically to study polarization data of the Milky Way galaxy and to look at those magnetic field angles. But in general is just a image processing software that measures the angle of a line. And Tom Shad from Maui also published a paper in 2017 where he demonstrated that this software worked very well for solar data, and he did this with AIA data. So the basic way that this works is you start with your initial data, you then have to process it through some sort of just generic high pass filter and turn it into a binary image, meaning it's either a 1 or a 0, where the ones are these sharp ridges that you want to actually measure. So once you create this binary image, you feed it into this so-called rolling Howe transform, or RHT, and it then measures what is the angle of this line with respect to the image. And it does this independently for every single pixel. It basically has a little box that it puts on every pixel, and it tries to fit a line to every direction, and it reports the relative probability of every possible angle. So what I did is do exactly this process for every usable eclipse image that we had going back for over the last 20 years, which corresponded to 14 eclipses. And for each eclipse, we actually often had multiple images at different angular resolutions, which could independently be processed. And so here's just an example of one image from each of those eclipses, where now I'm showing you the final data, which is basically the coloring there is showing you what the angle was inferred by this algorithm. And it's basically telling you what the magnetic field angle was, in this case, with respect to the image. So once you have all this data, you can actually go, oh, sorry, before I get ahead of myself. So we have some wider field images as well. These tend to be lower resolution, but can get you a much higher solar distances. So we have these different data that we can process independently. We also had a couple examples of really high resolution images from the 2008 and 17 solar eclipses. And you can see in these images that basically as we go to higher and higher resolution observations, we are able to resolve in higher and higher resolution magnetic field structure. And one of the surprising things coming out of these images was not only that how structured the corona is, but also that there appear to be largely open field lines throughout the corona. So you can clearly see there are some closed field lines like around streamers and active regions, things of that nature. But basically, a lot of these lines appear topologically open, starting at pretty much most latitudes around the sun. And this is somewhat surprising, at least often when you see model recreations of this sort of thing, they tend to sort of treat large regions of the equator as entirely closed. Now, some of the higher resolution models are starting to say things more along these lines, but anyway, I could get into that more later if we would like. So so the next thing to do is now that you've measured what the magnetic field angle is throughout the corona, you can then bin this data based on, say, distance and latitude, and you can get a plot like the panels in the middle there. So the middle panels are showing you as a function of distance and latitude on the sun, or rather in the corona, how far the angle of those field lines was from the radial direction. And this is important because models will often make assumptions about where the coronal magnetic field becomes perfectly radial and use that to magnetically model the corona. On the right-hand side is showing the same data, but again, in units of the uncertainty. So basically giving you an idea how certain we are that the corona was radial or non-radial during this eclipse. So the top panels there are from 2010, which is sort of near solar minimum. 2015 was much closer to solar maximum. And so these are sort of representative of what the corona typically is looking like at these different phases of the solar cycle. If you actually look at all the data at the same time, you can clearly see the solar cycle variation occurring over several years. In fact, this is over 2 different solar cycles. So solar maximum is sort of the first few panels at the top and the second to last row, whereas solar minimum is the middle and final row of these data. And so what you can see is that there's this sort of lobal type structure around about 40 to 60 degrees latitude north and south that occurs during solar minimum that are sort of tipped towards the equator. And this sort of structure is more or less expected if you consider the solar minimum corona to basically be a largely dipole and quadrupole magnetic moments. Whereas during solar maximum, you have a much more chaotic field, which indicates that you have higher order magnetic moments that are taking over. And so you have a much more chaotic magnetic field. So going back to, well, how radial then is the corona with distance on average? So if you average all latitudes and just ask, well, at what distance does the corona become entirely radial? What we're finding is, to a very high certainty, it's non-radial at least to about 4 solar radii. And this is a big discovery, because often models will assume that the coronal magnetic field becomes entirely radial at about 2.5 solar radii. So clearly from this data, that is a terrible assumption and will require a much larger distance in order to properly account for the magnetic field structure in the corona. So another thing you can do is, instead of looking at distance variation, is to look at latitude variation. So now this is averaging all the data between a distance in the middle corona of about 1.5 to 3 solar radii, and then looking at a function of latitude now over time. And what you can see is this, again, like this lobal structure I was talking about, which appears and disappears during different phases of the solar cycle. And if you know anything about the sun or how the magnetic cycle works, you might be guessing that this looks very similar to a butterfly diagram, which is like that on the left. So what this diagram is showing on the left is the magnetic field strength in the photosphere over the period of these solar cycles. And so really the data on the right there that we're getting almost looks like an inversion or you know, some sort of, it's definitely correlated with the butterfly diagram, but it doesn't look exactly the same. And so basically, I should mention, for the data on the left there, what it's actually showing you is, if you average over an entire rotation of the sun at a certain latitude, what is the average magnetic field vector for that region. And so then what I did was to take, for each eclipse, figure out what Carrington rotation was that, take the average magnetic field strength for that rotation, and then compare it to how radial was the solar magnetic field at that time. And you find there is a decent correlation, where for very, very curved magnetic fields, meaning very non-radial magnetic field, you notice that those will only occur when the magnetic field strength in the photosphere is rather weak. So that's the kind of right-hand side of this plot. Now, on the other hand, if you have a very, very strong magnetic field in the photosphere, that will only occur when you have a largely radial magnetic field. And you can even see that in the middle of this distribution, it sort of grows as you go to lower, or rather, as you go to a more radial magnetic field, you get stronger and stronger magnetic fields on average in the corona. Now, there is a decent amount of scatter here, and part of that is because we're averaging this over an entire Carrington rotation. Perhaps a future study could look at individual eclipses and do maybe some careful modeling and say, you know, what was the magnetic field strength directly below this structure, not necessarily the average for the entire rotation. But anyway, this is just sort of a first order, just showing that this effect is present and that more work needs to be done, clearly. So to wrap up these magnetic field results, we see fine scale structure visible down to the resolution limit of our observations. And this is sort of implying that we haven't yet probed down to the true resolution limit of the corona itself, meaning if we have better and better observations, likely we will be seeing even more fine scale structures. We also see what appear to be topologically open magnetic field lines that are occurring at most latitudes throughout the sun. Now, to be certain of this, you really need a proper magnetic field observation in terms of, you know, actually measuring the magnetic field strength, or potentially comparing this with modeling. So I'm not going to say concretely that these are open, but it does topologically appear to be the case. Another thing is this solar cycle variation that is occurring, especially in the middle regions of the corona with this sort of lobal structure that I talked about. Also that the corona, and I guess really the biggest result here is that the coronal magnetic field is highly non-radial out to at least 4 solar radii, and also is significantly non-spherical, meaning that at different latitudes, the distance at which you become radial is not the same. And modeling efforts actually have suggested that this is probably the case, and perhaps in the future should be the way that we do this sort of modeling. So now to wrap up just the entire project, I hope in the course of this talk, I've convinced you that bothering to travel to eclipses and making these sort of emission line observations, as well as the white light observations, are really a powerful tool to study both the corona and the solar wind. If you do this, you can measure things like the line to continuum ratio, which can allow you to infer the freezing distance in the corona for the ion that you're observing, which then, of course, could be useful for linking with in situ data far away from the sun in the heliosphere. Another thing is that if you can infer a line ratio, you can start to look at thermodynamic properties in the corona, and we were able to find time variation even between sites. So this motivates maybe especially for the 2024 eclipse to try to station people all along the path of totality and try to get an even larger baseline of these sorts of observations. Another thing would be to use, that we've used these white light observations to record the detailed structure in the corona, this magnetic field topology, which is a really powerful tool. And especially when you apply modern image processing techniques in order to understand what's going on a bit better. And this can challenge then modeling assumptions. So as Shadia mentioned, I will be sort of continuing this work along with Shadia and adding Cooper Downs as an advisor. And the idea here, or rather it's been funded for a postdoctoral fellowship. And so one of the first things I want to do, which I've sort of skirted around this, someone's echoing. I can hear myself echoing. I think someone's unmuted. The F corona then, sorry, let me start over again. So anyway, this work is planned as a postdoctoral fellowship. And so the first thing I want to do is use these different continuum channels to study the F corona color and potentially do a better job of actually extracting the structure and intensity of the F corona. Next thing I want to do is sort of the obvious continuation of this work, and indeed was sort of the original idea I had for this thesis, but along the way I realized there were many other things that had to be done first, each of which turned into its own paper. And the idea here is basically combine this tracing algorithm to automate the drawing of the magnetic field lines in the corona for the purposes of the freezing distance pipeline. Then at the freezing distance, quantify what is this ionic charge state ratio at the freezing distance. And then that tells you, or it predicts rather, in situ then what should the charge state ratio be. Finally, or not finally, the next thing I want to do is to take actually multiple lines, not just these two I've discussed at length, but to add some others which were successfully collected in the 2019 eclipse in Chile and Argentina, and actually to do a full, what we call a differential emission measure using multiple lines. And in this way, you can probe not just what the average temperature is along the line of sight, but you can actually get a better idea of what the temperature distribution is. Then finally, I want to take all of these observables and quantitatively compare them with, say, magnetohydrodynamic models, which is where Cooper Downs will be very helpful as part of this project. And so what we want to do is basically, in their modeling, is to synthesize the precise observables that we actually see during an eclipse, and then directly compare with the model, or directly compare then the prediction of what those observables should be with the actual observables. So one is, for example, the line to continuum emission, the temperature, as well as the magnetic field structure, say from the RHT pipeline. So at this point, I'll just do some acknowledgements. There are many people to thank, and clearly this is insufficient, but I just wanted to keep it kind of short. Obviously, thank you so much to Shadia, Milos, Judd, and Addy, and the rest of the Solar Sherpas, as well as the thesis committee. None of this work would have been possible without your many, many hard years of work and figuring out all these instruments, operating them, and giving me guidance along the way. A special thanks to Thomas Rimley and NSO and Aura for getting my funding over the last couple of years. Definitely would not have been able to complete all of these projects in such a timely manner and win the NSF fellowship without your support. Thanks as well to Bernie, Rand, and the rest of the UPS physics faculty for giving me a great foundation in physics and science and encouraging me to succeed. Thank you as well to Rob Jedicke for being my first advisor here at IFA and teaching me a lot of great habits, as well as continuing our collaboration in a sort of unique circumstance. And then, of course, thank you to every IFA faculty and staff member. There are so many to thank, so I'll just say a blanket thank you to everyone for all your help and over the years. And then, of course, thank you to my friends and family for all your support and many, many more. So at this time, I will stop for questions.
Okay, well, thank you very much, Ben, for a very comprehensive presentation. So I see that there are some hands raised. I think Jeff, would you like to go first? I saw your hand first.
Ben, thanks for a beautiful talk. So as you know, there are some people that are not convinced that the magnetic field is well aligned with, for example, filaments in the corona. How would you make the argument that the magnetic field that you're making conclusions about is well aligned with the density enhancements that we think of as the magnetic field structure from eclipse observations?
Oh, that's a really good question. Yeah, I think that's something that the whole field is sort of struggling with. And that's definitely something whenever especially when I've taken a solar course or something, I always ask, like, what do we actually mean when we say the magnetic field line? Because I think it's not an easy question to answer. We're sort of, like you say, we're assuming that these fine density enhancements perhaps are from the gyro rotation around the inherent magnetic field in the corona. Yeah, it's not entirely clear why that would necessarily be the case. I mean, especially if you consider, say, like a coronal mass ejection, clearly you'll have a non-radial field, say, at the front of the CME, because you'll have a density enhancement along say, in the wake of it. And so, but clearly that doesn't mean that field necessarily is still close to the sun. So, but it could be the case. I mean, I think fundamentally with the eclipse observations alone, I'm not sure that's something we can answer. Perhaps somebody like Parker Solar Probe, as they get closer, maybe they can start to address that if they can correlate, for example, say the density that they're seeing in the middle regions, or rather for them, the outer regions of the corona, say with the magnetic field. Yeah, I'm not sure how exactly to answer that question. I think that's something as a field that we have to reconcile.
Okay. Esther, you had a question?
Yeah, actually, some of the things that I was thinking about, you sort of got around to by the end of the talk. One of the things that I was really curious about is whether using the tilted filter strategy wouldn't provide some other difficulties in this. I mean, it must be hard to just even to calibrate that in general for separate systems, because generally when you tilt the filter, even though it's not a large distance, you not only affect where the peak is, but also you potentially can also slightly change the profile, even if it's
Yeah.
very, very large difference.
That's definitely the case. Yeah. So, well, thankfully, so with let me go back to that plot I showed earlier. It's buried under the sub things. So basically with these profiles, what I did was actually take the manufacturer profile, which if you are untilted would be centered right on that gray line. And so this is the profile if you model the tilting. So that they give you an equation and say, as a function of angle, this is what the transmission should be, or how you alter the wavelength. So these filters actually should be showing any warping from the act of tilting. But you're right, if you tilt it more, say if you want to make it all the way over to where that unique filter is, now you would be dealing with a decent amount of warping. Now there is a benefit, which is that these are to measure the continuum. So because the continuum is rather flat, actually if you do a solar disk calibration, you can kind of ignore the warping because it'll get accounted for in the calibration in some sense. And as long as the continuum source you're observing is relatively flat, which it should be over a few nanometers. But I kind of going off your point though, sort of once I figured out this is what was going on, I realized that this actually could be a really powerful technique to scan the corona in a three-dimensional sense. So if you had, instead of making these continuum imagers, say you have that unique filter by itself and you have your on-band filter, and then take those tilted filters and instead just tilt them less, or each have ones tilted at slightly different angles, you could actually try to scan the Doppler-shift corona. So you could maybe actually see what's coming at the observer and scan different Doppler shifts. So that's something I would like to do in the future. If possible.
You know that people who do narrowband work have done that, like particularly, I guess, people like Joss Bland Hawthorne, I guess, who was Brent student, who have
Okay,
been
yeah.
using that in Australia for actual other purposes. I just assumed that wasn't in. You have temporal constraints here in terms
Yeah.
of when you
Right.
work. I didn't want to turn that in, but I wanted to say as well that your result about having more than going out beyond 2 solar radii for observing the assumption about radial modeling, that I think you already saw that in the plots where you were trying to model things, the one where in the upper left you had that, where you had the closed loop and
Oh yeah, here.
Even there, the fact that bound loop status, and I guess one doesn't quite see it in terms of the same distances. There were already hints that you weren't going to be able to get these well-behaved radial modeling close into the sun. I mean,
Right.
just seeing data like that. And I had been curious about something you alluded to for the future work, which is that the coronal lines, the iron lines, are sort of very, very well known for people who work in lots of other areas.
Sure, yeah.
And I was wondering whether, in fact, you weren't going to try a similar project for something like at 6374 rather than 5303.
6374. Which line is that?
Iron 10.
10.
Oh,
iron
okay.
10. Usually iron 10 and iron 14 are some of the strongest ones that we see from things like X-ray observations of things.
So actually, we do measure that. I believe we have that data actually for the 2019 eclipse. So for I think the 2019, we measured iron 9, 10, 11, 13, and 14. So that's where I'm saying I want to do the actual temperature distribution kind of stuff. So yeah, actually, if you do I showed that slitless spectrograph at the beginning. If you actually look at the entire spectrum, if you don't crop it, you see iron 10 as well. So the two that you see with a very rudimentary instrument are iron 10 and iron 14. I think the reason, say, in the 1800s eclipse, they weren't able to see that because it was far enough out that the photographic plate just didn't have sensitivity at that wavelength.
Yeah, I figured that some of this was also trying to choose the wavelength regions where you're getting, maximum signal.
Absolutely, yeah. So that's where, like, we could, for example, like iron 12 in principle should be one of the most abundant lines in the corona, but it's not. I can't remember the wavelength off the top of my head, but it's outside of the sort of visible near IR range, so it's not easily observable during an eclipse, which is a real shame because it actually should be the brightest if it were in the range that we could observe.
So one more quick question, and I'll let you go on. But given that your knowledge about temporal variations is probably coming from making different observations along the path of the eclipse, how much do you know about temporal variations in some of the structures that you're seeing from the actual eclipse data, where you were taking this from different stations?
Well, I would say that part of the problem, and this also was I used it already, but the bane of my existence was figuring out why these things were changing the way that they were. And so part of the problem is, you're dealing with, as I said, an already perturbed state. So it's like, if you have something that's not in equilibrium and you're watching it evolve, that's very hard to infer, well, where did it start from, right? So I think, when you have things like LASCO or even, well, AIA, I would say, in the low corona has done exquisite amount of work about time variation with, say, active regions and the formation of CMEs. And so, like, there's a ridiculous amount of papers that are coming out about that sort of thing. The problem is, in this region of the corona, there's not a whole lot of great data. And then if you go into the outer corona, now you only really have white light observations from LASCO. Now, there are going to be things like Solar Orbiter, which is, I'm not sure of the exact status right now, but it should be online now, as well as Proba 3. Anyway, these two telescopes are going to be in space, and they're going to have a coronagraph. But not only white light, they will have a few narrowband filters. But I think it's a real shame, actually, that they don't have that many narrowband filters. They have, I think, I can't remember which is which now. It's all in the thesis, of course. But basically, one of them has like an iron-14 emission line, but no continuum pair. And then it has like a hydrogen or helium line, but no pair. And then that's it. So you say, okay, well, maybe you can model the continuum, you know, especially if you build up a lot of data, et cetera. But even if you can model the continuum and do a line to continuum ratio, they could do time variation of that. They could potentially measure the freezing distance, but they could not measure, say, a temperature distribution, because if you're just looking at just the iron-14, that tells you nothing really if you don't also have, say, iron-11 or iron-10 or something. You need that, and it's what you do in galaxies all the time, is taking line ratios and saying, you know, what is it, putting it on some diagram and saying, where is it on this diagram? Like, that's a really powerful technique. But if you only have the one line or two lines that are of different elements that now you have to account for an elemental abundance, which also has dynamics in the corona I'm not going to get into, but different parts of the corona even will have different elemental abundances. So then it gets even more complicated to get anything out of it. So I would say if I had unlimited resources, I would actually say we should build a spacecraft that has a whole suite of narrowband filters, or potentially a big one that you could rotate to an arbitrary angle, and make these sort of observations constantly. Even with like a LASCO quality data, which is launched in '95, even with that quality, with a nice narrowband filter, you could do a lot of powerful work, I think. In fact, LASCO C1 was supposed to do this, but it failed, unfortunately, rather quickly after launch. So in some sense, a lot of this work may not have been novel if LASCO C1 had not failed.
Okay, thank you. So Dave Tholer, next.
Okay, that was a nice picture of Comet Neowise that you showed at the beginning of the presentation. And it got me wondering about the material in the plasma tail. Do you know what the typical velocity for that material is, both in a heliocentric and a comet-centric reference frame?
Ooh. The comet-centric one, I'm not sure. And obviously that'll depend on the comet. So order of magnitude, the solar wind speed at large distances, say more than a third of an AU or something, are typically between about 400 and 800 kilometers per second. So my intuition would be that the ion gas tail should be, since it's locking on to the solar magnetic field, rather the solar wind's magnetic field, it should be probably traveling about that speed, so hundreds of kilometers per second. However, I suppose there would be some amount of acceleration needed as well. That's a really good question. I'm not entirely sure. I do know that there are some people who work on this sort of thing. But yeah, so some people have tried to actually use the ion tail to study sort of the time dynamics of the solar wind as because it's sort of imprinting the solar wind that's affecting as it's flowing outward at different times. But I know it's a rather complicated process. I know, in fact, Yudish has done some work on that for his thesis. But yeah, I'm not entirely sure.
Okay, thank you.
Cooper, greetings. You're next.
Hi, how's it going? Great talk, man. I really enjoyed it. And I think Esther's question actually set me up pretty well. Just one quick comment. I want to emphasize how important these types of eclipse observations are. Right now, it covers part of the corona that we can't observe well. But even if we could from space, the fact that you can design your experiments every single time there's another eclipse differently and in these creative ways that you've illustrated in their talk, that's essential. And I think that will never go away. So it's really cool to see these observations. And I'm really thrilled that you'll be continuing with it. But then on to my question, I do hope through our collaboration that maybe I can convince you that models aren't entirely bad. In particular, that AIA or other types of EUV emission aren't entirely bad either. And that pertains to then my question about your second project, about the changing temperature in the corona.
Mm-hmm.
And it's really striking, your argument that the entire corona should be changing over such a short window. That's half an hour. And, you know, I guess the sun rotates by ½ degree or less during that time. But something like a filter ratio, especially low down where your significance is very high, it seems like you should be able to do that with EUV data. And I may have given you a hard time at AGU once about this, but you actually end up trying to corroborate that by looking at EUV emission.
Yeah, that's a really excellent question. And I just want to say, first of all, I'm not at all saying that the EUV or the models are not useful. I was just trying to highlight where their limitations are.
Sure.
Like where they hit sort of the limit. And that's where I think, again, yeah, the cross interplay between all of these different observations and the models is essential, because, like, for example, if we had just had this data, but there was no AIA and there was no LASCO, we would have not a clue why it was doing this. And people would probably say they don't believe it at all, which I already get sometimes. So, but to counter your argument about these changes, so maybe I should have said it differently, where it doesn't necessarily mean that the entire corona is changing. So hypothetically, let's say that 80% of the corona stayed precisely the same, hypothetically. But now you have a CME that's propagating along the line of sight, moving at a few hundred kilometers per second. At that speed, you can get, if you're going, say, perfectly radial, or rather in the plane of sky is what I'm trying to say, you would move, I did the math in the paper, I think it's about half a solar radii in 30 minutes. So that means that whatever plasma was, say, at 1.5 solar radii now could be at 2 solar radii. And if you're coming out of the plane of the sky, if you're moving fast enough, I mean, these filters are so narrow that if you're moving faster than about 150, 200 kilometers per second, you actually shift out of the bandpass, meaning that we're actually scanning a very narrow region near the plane of sky. So if that plasma distribution has a relatively dense component that's propagating through the plane of sky, maybe it's or out of the plane of sky, maybe it's expanding, those could be driving these changes. So it could entirely be that the lower regions of the corona didn't change at all, and that we are just seeing line of sight effects where we have the CME expanding. In that case, you would actually not expect the EUV to really change, because the EUV is very preferentially seeing the low corona given the collisional excitation. So what that means is the low corona maybe doesn't change at all. Maybe it's sort of ignorant to what's going on in the outer corona. And so what we are probing is really different. And that, of course, is a big challenge with these sort of line of sight observations, is you're not actually sure where precisely the plasma is located. You know, like in terms of the 2D space where it is, but you don't know in the 3D space. So that's where I think, especially say in 2024, if we can have multiple of these tilted imagers at different wavelengths, say, ideally, I was thinking if you had 10 of them or something at plus or minus, plus 50, plus 100, plus 250 different kilometer per second offsets, you could try to actually scan the corona as a function of depth as well as area. And in that way, you could maybe answer some of what you were asking about, why does the EUV not change? But still, I mean, the EUV does change a bit. So for example, here's just more evidence of the CME. So what these panels are showing in the top is actually the absolute difference in intensity from the LASCO C2 data. And so you can see there's a spike at the middle left panel there, and then a decrease. So we think that's probably the signature of this halo CME going through the field of view. And actually, a few days later, you see at the bottom there is the helium abundance measured in the solar wind with ACE, which is at about 1 AU. And a few days later, it sees a big spike in the alpha abundance. And if you assume a linear propagation speed, that corresponds to roughly 550 kilometers per second, meaning that this is a signature of that halo CME passing. And I should note, alpha abundance has been correlated with CME activity as well. Anyway, so the point is that I think there's a lot more going on here, and you're probably right that the EUV isn't totally changing. And that would be, I think, a good next step would be to somehow stitch these data sets together in a more complete way. I guess I'll show this too. This is the disk center active region at a few different AIA wavelengths, showing the changes during the eruptive period before the eclipse.
Okay, thank you. So Sushant, you had a question?
Yeah, great talk, Ben.
Thank you.
Congratulations, you did great work. I wanted to ask you about the slide that you had where you had the photospheric magnetic butterfly diagram on the left and the tilt angles on the right, as in like the alignment angles, I think. Yeah, the alignment of the field with respect to the radial direction.
Oh, wait.
That was it. Yeah.
Okay.
So does this suggest that the field angle is higher in active regions? Sorry, the y-axis isn't aligned, so I can't exactly tell.
Oh, you're right. Yeah, that's. I think I threw this together just for the slide. This isn't as it appeared in the paper. Yeah, so basically the more or less the really dark regions of the right-hand diagram, which show you where the field is very curved, those basically line up with sort of the weakest regions in the butter. So basically those yellow regions, in a sense, it's like the opposite of the butterfly diagram. So it's actually in the locations where there were not any active regions.
Okay. And did these field angles have a preferential direction? Do you have the data for that?
Yeah, so I put it just in terms of radial because it becomes a relative thing where you talk about the direction, but then if it's east versus west, it'll be inverted, and north versus south and that sort of thing. So I ended up just putting it in terms of the actual absolute difference from radial. But I do have that data. And that is something I would, in the future, would especially like to work either with Cooper or potentially with somebody else on directly comparing, the precise angles that we're seeing at locations in the corona and comparing that either with MHD and or PFSS type models.
I think that would be really important. This could these tilts could have something to do with the flux transport processes and how the polar field builds up.
Right. Yeah, that very well could be.
Yeah. Thank you.
Thank you. Ready?
Okay. Oh, well, very, very good talk. I just have a quick question. When you have after the freeze in distance, you have a certain composition of the ions. When you measure these ions, say with Ulysses far away, you get different values. Is that because they look at the different times when these particles erupted from the sun?
Yeah, essentially. So if in general with any in situ spacecraft, you're seeing a time, essentially, if they think about the sun as being like somebody holding a hose and they're squirting out the water, and if someone at the source of the water is constantly changing the temperature, if you're sitting far away and you're just measuring as the water's going by you, you're measuring the temperature, you'll see it go up and down and fluctuate and whatever. So what that's telling you is how was it changing at the source when it was released. So the idea being that, you're seeing the time variation. For example, if you were to co-rotate with the sun in some way, you could maybe measure it over a single structure. What's this time variation? More often, though, you're orbiting at some arbitrary speed, and so you're actually shifting relative on the longitude and latitude on the sun. So really what you're seeing is at least normally with Ulysses data, it's often displayed simply as here's what the average was at different latitudes over our whole orbit, which is many years of data. So what I'm hoping to do, say, for this linking idea is even compare it with Ulysses data, because Ulysses says, during solar maximum, here is a typical ion abundance ratio that's seen at this latitude versus solar minimum. And then we can maybe do that in the corona and do a statistical comparison to say, when there's these type of magnetic structures like a coronal hole versus a streamer, what type of solar wind do you see in situ? And hopefully we can sort of match the same behavior in the corona.
Thank you.
I think, John, are you IFA instrumentation? Hello? So who's IFA instrument?
Oh, that's me. This is Hao Seng. Sorry. Ben, great work. Congratulations.
Thank you.
And a simple question is, we all our data taken here is line of sight integrated, and I just wonder if you take that into account, how would that affect your conclusion on various analysis, and
right.
Possible to put a quantitative number on it, make some assessment of.
Right. So I sort of talked about that a bit with the specifically with the temperature analysis, in the sense that because we have a narrow bandpass, we can at least quantify that the plasma we're seeing has to be below some velocity in or out of the plane of sky, meaning that we are, and then combine that with the fact that, of course, the corona is decreasing in density with distance, which means if you're at some really high angle, the intensity will be far lower than it will be near the plane of sky. So if you combine those effects, basically for the narrowband observations, you can quantify sort of what thickness that is, I guess. But the problem is, of course, it's velocity, not spatial. So you'd have to make some assumption, I guess, about the expansion speed in the corona in order to really turn that into some physical distance. But certainly that's, again, where if you have more of these tilted filters, you could do a better job maybe of quantifying that sort of thing. As for the, say, the white light observations, those are very broadband. So now you could actually see structures at any arbitrary distance from the sun. But again, because the density is dropping so rapidly with distance, you're still sort of seeing just near the plane of sky. I think in the paper, we sort of waved our hands and said it's within about 20 degrees of the plane of sky. You wouldn't expect something at 80 degrees to be really contributing. But yeah, no, that's a good point. Is how could we quantify that better? Yeah, I'm not entirely sure. I mean, if we had, for example, unlimited observing time, the real thing to do would actually be to measure these lines with polarized filters, and then you could do a more complete census, but we just don't have the observing time for that, unfortunately.
Okay, thank you.
Okay. Any other questions from the audience? No? Okay, well, thank you all for attending, especially for those of you who had to get up early. And if the attendees could log out, and then we'll restrict the group to the committee.